Petersburg, she'll speak on operator error estimates for homogenization of elliptic systems with periodic coefficients. Please.
Thank you. So, first of all, I would like to thank the organizers for the invitation and for the opportunity to give the first morning talk after the conference dinner. I think it means that Sasha and Lyonya trust me a lot. Well, I'm going to talk about operator error estimates in homogenization theory. This is the outline of my talk, and we will start with a short introduction. First, some notation. By gamma, we denote a lattice in RD. Omega is the cell of this lattice. For instance, if gamma is the cubic lattice ZD, then omega is simply the unit cube. We use the following notation, which was also used yesterday in the talk by Valery Smyshlyaev. Here, epsilon is a small positive parameter. If phi is a gamma periodic function in RD, then this function oscillates rapidly for small epsilon. And homogenization theory studies differential equations with such rapidly oscillating coefficients. Next, let O be a bounded domain of class C11. And first, let us consider a typical example of homogenization problem. In this bounded domain, we consider the divergence type elliptic equation for U epsilon. Here, the right-hand side is a given function in L2. And on the boundary, U epsilon is equal to 0. We are interested in the behavior of the solution for small epsilon. It turns out that there exists a limit, U0, as epsilon tends to 0, limit in L2. This limit function is the solution of the so-called homogenized problem or effective problem. Equation with the same f and also Dirichlet boundary condition. Main questions. Main questions are the following. To find the effective matrix G0, to estimate the error term in L2, and also to find approximation of the solution in the Sobolev space, that is in the energy norm. For this, we have to add some character to U0. And today we will discuss error estimates of the following form. The L2 norm of U epsilon minus U0 is less or equal than some constant multiplied by epsilon and the norm of f. Let it be estimate 1. This estimate is order sharp, and on the right hand side we have the norm of f. And of course we can formulate this in operator terms. We denote this operator by a d epsilon. D means the Dirichlet condition. And let this operator, the effective operator, be a d naught. Then we can rewrite estimate 1 as follows. The L2 operator norm of the difference of the inverses is less or equal than C multiplied by epsilon. And such estimates are called operator error estimates in homogenization theory because they can be formulated in operator terms. Such estimates were intensively studied during the last 15 years. I will give a short survey, but a little bit later, after formulation of the results. So today I would like to present recent results obtained last year on operator error estimates. We study operator A epsilon, which is a matrix strongly elliptic operator with rapidly oscillating coefficients, second order and self-adjoint. We study this operator both in the whole space and in a bounded domain with the Dirichlet or Neumann boundary conditions. We will approximate the resolvent of this operator in a regular point zeta in the L2 operator norm and also in the norm of operators acting from L2 to H1. This approximation will be with the corrector. And we find two parametric error estimates. With respect to epsilon and this spectral parameter zeta. Well, now I proceed to the precise statement of the problem. So we study second order operators, matrix operators of size n by n, admitting the following factorization. Here, G epsilon is a rapidly oscillating matrix valued function of size m by m. B of D is the first order operator of size m by n. Then B star.
Operator A. Yes.
Huh?
It is operator A, isn't it? A epsilon.
Yes, it will be. Okay. Now it's differential expression. Yeah.
He says an epsilon is a particular case. Epsilon, as you have written it, is a particular case.
Yes, this operator, I will call it the acoustics operator, the elliptic divergence type operator. The acoustics operator, it's particular case, yes. And
B is grad and B is...
This is a wide class of matrix operators, which includes also the operator of elasticity theory and other interesting examples. First, it was studied in our joint papers with Mikhail Birman. So G of x is a Hermitian m by m matrix valued function, in general with complex entries. It is periodic with respect to the lattice gamma, bounded and uniformly positive definite. We don't need any smoothness assumptions. B of D is the first order differential operator with constant coefficients of this form. BL are constant matrices. We consider the symbol of this operator, B of xi, and assume that this symbol has maximal rank. So it's a matrix of this size and the rank is equal to n. More precisely, if we study the problem in the whole space, or if we study Dirichlet problem in a bounded domain, then we assume that the rank of the symbol is equal to n for any non-zero xi in Rd. If we study the Neumann problem, then we assume the same for any non-zero xi in Cd.
This implies that m is greater or equal than n, right?
M is greater or equal than n. Didn't I write it?
No.
M is greater or equal than N. Yes, sorry. M is greater or equal than N. So, we study the operator A epsilon in L2 RDCN. It will be A epsilon, the operator given by this differential expression. And we study two operators in L2 OCN, where O is our bounded domain of class C11. It will be AD epsilon, this operator with the Dirichlet condition, and AN epsilon, this operator with the Neumann boundary condition. Of course, the precise definitions of these operators are given in terms of the corresponding quadratic forms. And under our assumptions on G and on the symbol, these quadratic forms are coercive, the operators are self-adjoint and non-negative. Our goal is to study the resolvents of these three operators. Okay, now, in order to formulate the results, we have to define the effective operator. The effective operator is given also in a factorized form. And now G naught is a constant positive definite matrix called the effective matrix. And we recall the definition of the effective matrix. The definition is non-trivial. First, we consider an auxiliary problem, which is usually called the cell problem in homogenization theory. By lambda, we denote the solution of the following elliptic equation. This is equation for lambda. Lambda is matrix valued n by m and periodic. So we can consider this equation on the cell omega, on the cell of the lattice with periodic boundary conditions. Lambda is periodic. Then the solution exists and is defined up to a constant summand. We can fix the choice of the solution by the condition that its mean is equal to 0. And the effective matrix is defined in terms of this solution as the mean value of this matrix valued function. G naught is defined by the following formula. It turns out that this matrix is always positive definite. Note, it will be important in what follows, note that this lambda, the solution of the cell problem, always belongs to the periodic subspace of H1 omega. But in general, it is not bounded. In some cases, we know that it is bounded when dimension is equal to 2, and also for the acoustics operator, it is bounded. But for general elliptic systems, it is not. And some technical difficulties are related to this fact. Well, now, by A naught, we denote the effective operator in the case of the whole space. AD naught will be the effective operator with the Dirichlet condition, AN naught with the Neumann condition. And now we are ready to formulate the results. We start with the results in the whole space. Theorem 1. Let zeta be a complex number it belongs to C minus the positive semi-axis. This point is regular for both A epsilon and for the effective operator. And for any positive epsilon, we have the following estimate for the L2 operator norm of the difference of the resolvents of A epsilon and the effective operator in the L2 RD operator norm. On the right we have C of phi epsilon divided by the square root of the modulus of zeta. What is phi? Phi is the angle, the argument of zeta. This constant depends on phi, and it grows when phi is small. But in any sector,
how do you define argument?
From 0, between 0 and 2 pi, the argument of zeta.
So when it is small and when it is close to 2 pi?
Yes, when it is small and when it is close to 2 pi, yes. If this is some arbitrary phi naught, and we take such sector, in this sector estimates are uniform. In this sector we can take one and the same constant. If we fix zeta, then we obtain estimate of sharp order with respect to epsilon. But if we take large zeta, the order is better because of this square root of the modulus of zeta. Well, next theorem gives approximation of this resolvent in a different operator norm, in the operator norm from L2 to H1. And we have to define the character. The character K depends on epsilon and zeta. It contains the resolvent of the effective operator, B of D, F epsilon, and lambda epsilon. Lambda epsilon is multiplication by the rapidly oscillating function, lambda of x over epsilon. This S epsilon is called the Steklov smoothing operator. It plays auxiliary role. The Steklov smoothing is defined by the following formula. We need to include this operator because lambda in general is unbounded. If lambda is bounded, then we can use a simpler character, the standard character, K naught, which doesn't include this smoothing operator. But in general, it is necessary to include the smoothing operator in the character. And this operator, K, is continuous from L2 to H1. But the norm of it is large. The norm of the character is of order 1 over epsilon. This is because of the presence of rapidly oscillating factor. Well, now we can formulate our second result, theorem 2. Under the same assumptions on zeta, we have the following approximation for the resolvent with the character taken into account. This is the character term. The operator norm from L2 to H1, and we obtain estimate by C of phi. This depends on zeta and epsilon. estimate 4. Again, this estimate is uniform in any such sector. And if we fix zeta, then we have sharp order estimate with respect to epsilon. So these are the results in the whole space. Yeah.
Operators A epsilon and A naught.
Yeah.
They are self-adjoint.
Self-adjoint.
But all of a sudden this funny K appears, which of course doesn't look like it is anything self-adjoint. Or
No, the operator norm is from L2 to H1. We have such result from L2 to L2 with a different character, which is self-adjoint. But here we have operator norm from L2 to H1, so no contradiction.
Okay.
Now I will formulate the results in a bounded domain.
Is it all right that it doesn't blow up at 0, the right-hand side? Does it blow up? Oh, yes, it does.
For small zeta,
It does, sorry.
this is large. Yeah. Okay, so results in a bounded domain, theorem 3. We again assume that zeta belongs to the complex plane minus positive semi-axis, and in addition we assume that the modulus of zeta is greater or equal than 1. Then for sufficiently small epsilon we have the following estimate for the difference of the resolvents of a d epsilon, the Dirichlet operator, and AD, and the resolvent of the effective operator in the L2O operator norm. On the right, we have again this C of phi. Epsilon divided by the square root of the modulus of zeta. This term is the same as in the case of RD, and plus epsilon squared. 5, estimate 5. The same is true for the Neumann case. If we fix zeta, we obtain estimate of sharp order. And in fact, this theorem is the main result, because it's not easy to prove such sharp order error estimates in a bounded domain. Also, the estimate is uniform in any such sector.
There is no special zero for Neumann, since zero is an eigenvalue, right? For
the modulus of zeta is greater or equal than 1 now,
okay.
in addition.
Fine, okay.
Yeah. Well, next theorem will be about approximation with the corrector. So we introduce the corrector, Kd of epsilon zeta. Again, it contains the resolvent of the effective operator. Next, PO, its extension operator, D of D, smoothing S epsilon, and multiplication by lambda epsilon. What is PO? It's a linear continuous extension operator from each HS in the domain O to HS in RD. In fact, we need this property for S equals 0, 1, and 2, but we can take the universal extension operator, which exists. theorem 4.
What do you mean universal? But it is not uniquely defined, is it?
No, we fix it somehow.
And the answer is not going to depend on this choice.
So the character depends on the choice of this extension operator, yes.
But you will have to explain that.
If you take a different extension operator, then the norm of the difference goes to error term.
So the answer doesn't depend on the choice.
The character depends on the choice, but if you take a different extension operator, estimate will be of the same order. The constant in estimate will change only. Yeah. Also, this character is continuous operator from L2 to H1. If we know that lambda is bounded, we can use a simpler character. If lambda is bounded, for example, for the acoustics case or for the two-dimensional case, lambda is bounded, then we can use a simpler character, the standard character, which doesn't contain extension or smoothing. And similarly, of course, we define the character for the Neumann case in a similar way. Now, theorem 4. Under the same assumptions on zeta, we have the following approximation for the resolvent of our operator in the L2H1 norm. But now we have another order of this estimate. Square root of epsilon divided by the modulus of zeta to 1/4 and plus epsilon. So for a fixed zeta, it is of order square root of epsilon, which is worse than in theorem 2 for the case of AD. This is explained by the boundary influence. A similar result is obtained for the Neumann case.
Is it really possible to extract another term, another kind of character that would be responsible for the boundary?
Yes, I will do it in the proof. I will introduce some boundary layer correction term. If we take it into account, then the estimate will be better. But it's not simple, this boundary layer correction term.
Alex is asking if you can, by adding extra boundary corrector to the left-hand side, to improve the error.
Yes, we can. We can. Yeah, we can.
You can. So,
We can.
Why is it not there?
for this you need to construct.
It's complicated.
This character term is complicated. It is solution of the differential equation with rapidly oscillating coefficients.
They're all solutions with.
No. No. Here the character contains the resolvent of the effective operator. And the dependence on epsilon is only in this factor.
If you wanted to say it is not complicated, explicit. Yeah. It doesn't have any similar structure.
Well, this boundary layer correction term will appear soon when we will discuss the method. Okay? And the last theorem gives a little bit different approximation. And in this last theorem, we will lift this restriction that the modulus of zeta is greater or equal than 1. So let me formulate the last result. But I will formulate it for the Dirichlet case. For the Dirichlet case. Theorem 5. We know that the operators with the Dirichlet boundary condition are positive definite. So we take a number C star such that it is a common lower bound for AD epsilon and for the effective operator. For example, this C star can be taken a little bit smaller than the first eigenvalue of the effective operator. And now we assume that zeta belongs to the complex plane minus semi-axis from C star to infinity. So we can take zeta near to the bottom of the spectrum. Then for small epsilon, we have the following estimates. The first one is for the difference of the resolvents in the L2 operator norm, estimate of order epsilon. I will define this C of zeta in a moment. The second is approximation for this resolvent with the corrector taken into account in the operator norm from L2 to H1. This estimate is of order square root of epsilon. This C of zeta is of order 1 over zeta minus C star squared near the point C star, see here, and C of psi outside this disk. Psi is again the angle. Now it's argument of zeta minus C star. And also estimates are uniform in the corresponding sector, where psi is between some psi naught and 2 pi minus psi naught. In fact, this result is rough with respect to zeta, but nevertheless we can use this result if zeta is near to the bottom of the spectrum, and we can use theorems 3 and 4 if zeta is large.
Not optimal.
Not optimal. You can compare with the case of RD. It's not optimal with respect to zeta. In theorem 3, it's optimal for large zeta. Well, so here are the results, and now I will give a short survey. What was known before. In a series of joint papers with Mikhail Birman, starting from 2001, an operator theoretic approach to homogenization problems was suggested, and we studied with Mikhail Solomonovich, we studied the problems in the whole space in RD. Such matrix elliptic operators in RD. In particular, the results of theorems 1 and 2 for a fixed zeta were proved for zeta equal to -1. The method was based on the scaling transformation, Flakier-Bloch theory, and analytic perturbation theory. A different approach to operator error estimates was suggested by Vasily Vasilyevich Zhikov, and also is in his joint works with Pastukhova in 2005 and 6. They studied two particular operators, acoustics and elasticity. They obtained the results in the whole space, but by a different approach. And also they studied the problems in a bounded domain with the Dirichlet-Neumann boundary conditions. Their main result was approximation of the inverse operator. I will write for the Dirichlet case, but they have also the results for the Neumann case. They obtained approximation with the corrector in the operator norm from L2 to H1 with error term of order square root of epsilon. So in their work, first such error estimates appears, and they realized that the estimate in a bounded domain is worse than in AD due to the boundary influence. As for estimate in L2, they obtained estimate also of order square root of epsilon as a rough consequence of this one. But it was not order sharp, and a natural problem was to improve this L2 error estimate. This was done by Grisot. There are two papers. Grisot studied only the acoustics operator, the elliptic, scalar elliptic divergence type operator with real valued coefficients, and in 06 he proved sharp order L2 error estimate. Estimate of order epsilon. Let it be estimate 9. Using the unfolding method. For elliptic systems, such result was obtained independently by Koenig, Lin, and Shen, and by myself. In 2012, Koenig, Lin, and Shen proved estimate 9 for uniformly elliptic systems. Also for the Neumann condition. But it was assumed that the coefficients are Hölder continuous. Such assumption is unpleasant for homogenization problems because in applications we deal with discontinuous coefficients.
I think, yes, they have more restrictive coefficients, but I think less regular boundary.
Less regular boundary, but for less regular boundary, the estimate was not order sharp. It was some log of epsilon for less regular boundary, yes. For smooth boundary, they proved sharp order estimate. Note that the class of operators that we consider is much wider than the class studied in this paper, and we don't assume any smoothness of the coefficients.
Actually, they have also less general elliptic systems. I don't think
Less general elliptic systems. They
and
yes.
they didn't have strong ellipticity. Just
For example, elasticity, the elasticity operator doesn't belong to their class, but belongs to our class. And the class of operators that we consider in a bounded domain was studied in during the last 3 years by myself, and one paper is joined with my student Misha Pakhnin. First, such estimates, like in theorem 3 and 4, were proved for a fixed zeta, and finally, last year, such two-parametric error estimates were obtained. Well, now let us discuss the method. theorems 1 and 2, they can be easily deduced from the results of Biermann and myself in a fixed point with zeta equal to -1. By using appropriate resolvent identities and the scaling transformation. This is not difficult, but such a simple way is impossible in a bounded domain. So, for the proof of theorems 3 and 4, we study the associated problem in the whole space. Next, we introduce the boundary layer correction term and carefully analyze this term. Some technical tricks are borrowed from the paper by Zhikov and Pastukhova, in particular using the Steklov smoothing operator. Biermann and me, we used a different smoothing operator, and it was suggested by Zhikov to use the Steklov smoothing, which is convenient for the study of problems in a bounded domain. So let us discuss the proofs of theorems 3 and 4 for the simpler Dirichlet case. Let f be a function in L2. By u epsilon, we denote the solution of the Dirichlet problem with the right-hand side f. U naught is the solution of the Dirichlet, of the effective Dirichlet problem with the right-hand side f. U naught tilde is extension of u naught to the whole space. Since the boundary is smooth, u naught belongs to the Sobolev space H2, and this u naught tilde belongs to H2 in RD. Next notation is the first order approximation to the solution u epsilon. That is the sum of u naught and corrector in order to prove theorem 3, we have to estimate the L2 norm of u epsilon minus u naught. In order to prove theorem 4, we have to estimate the H1 norm of u epsilon minus the first approximation v epsilon. And first, we consider the problem in the whole space, which I call associated problem, the problem associated with our initial Dirichlet problem. We take this u naught tilde, which is a function in AD, apply our operator a naught minus zeta, and denote this as f tilde. This f tilde is a function in L2 AD, and its restriction to the domain O is f. And let u epsilon tilde be the solution of this equation in AD. This is the problem which we associate with our initial problem. We have theorems 1 and 2. We can apply them and obtain nice approximations for this u epsilon tilde with sharp order error estimates, both in H1 and in L2. And next step is to introduce the boundary layer correction term. It is denoted W epsilon. it is the solution of the homogeneous equation, but with rapidly oscillating coefficient, d epsilon. And non-homogeneous boundary condition. On the boundary, this W epsilon is equal to the character. If we take it into account, we obtain nice estimates. So we consider U minus V plus W.
It's this W epsilon which is responsible for the boundary effect.
Yes, it's called boundary layer correction term. If we add it, this function is in H1 0, it is equal to 0 on the boundary. It is possible to control the norms of this function in terms of this associated problem. In terms of the norms of such function. V epsilon tilde is the first order approximation for U epsilon tilde. There is a relationship between this function and the problem in AD. So using theorems 1 and 2, we obtain nice approximations for this function in H1 and in L2 with sharp order estimates. The number 10, 11. So we see that if we estimate, if we manage to prove appropriate estimate for H1 norm of W, we will prove theorem 4. If we manage to prove appropriate estimate for the L2 norm of W, we will prove theorem 3. So the problem is reduced to estimation of this boundary layer correction term. And first, we estimate the H1 norm of W and prove theorem 4. And next, using the already proved theorem 4 and some duality arguments, we will prove theorem 3. So next step is to find estimates for the H1 norm of W. Lemma 1, the H1 norm of W satisfies estimate of order square root of epsilon divided by the modulus of zeta to 1/4 plus epsilon. Clearly, times the norm of times the norm of F in L2. Clearly, if we apply this lemma together with estimate 10, we immediately, oh, thank you, yes, the norms of F in L2, of course. It's not operator, it's a function. It must be the norm of F in L2 here, yeah. So, lemma 1 together with estimate 10 directly imply theorem 4. Okay? Let me comment on the proof of this lemma. Here we use localization near the boundary. We consider the epsilon neighborhood of the boundary. We fix a cutoff function, theta epsilon, which is C0 infinity. It is supported here near the boundary. It is between 0 and 1. And on the boundary, it is identically 1. So we fix such cutoff function. We take our corrector and multiply it by this cutoff function. Denote this product by phi epsilon. This function is supported near the boundary. It's possible to estimate the norms of it using the properties of lambda, the properties of the smoothing operator, some technique about estimates near the boundary. And it's easy to show that the norm of W in H1 is controlled in terms of the norms of this function. And this way we can prove lemma 1. And so theorem 4 is proved now. And next step is to estimate the L2 norm of W and to complete the proof of theorem 3. Estimate for the L2 norm of W. Lemma 2. The L2 norm of W satisfies the following estimate. Very good, nice estimate, sharp order. Clearly, lemma 2, together with estimate 11, directly imply theorem 3. Now let me comment on the proof of this estimate. We consider the difference, W minus phi. It is equal to 0 on the boundary. It belongs to the class H1 0. We can write down the integral identity for this function using the fact that W is solution of the homogeneous equation. So the right-hand side will be the following. There will be only the terms with phi. Let us denote this right-hand side as I epsilon of eta. This integral identity is valid for arbitrary eta, test function eta in H1 0. And the crucial point is to substitute here eta equal to eta epsilon, which is the solution of the Dirichlet problem with some right-hand side phi. And here we have the point zeta bar, where phi is in L2. If we substitute such eta epsilon here, then clearly the left-hand side is equal to the inner product of W minus phi and this capital phi in L2. So if we manage to obtain appropriate estimate for this functional for the right-hand side, we can derive estimate for the L2 norm of W minus phi. And when we estimate this term, we use theorem 4. We use approximation for eta epsilon in H1. We prove appropriate estimate for the right-hand side and derive estimate for W minus phi. the estimate for the right-hand side will be the following. Here we have the norm of f and the norm of phi in L2. In the proof, we apply the already proved theorem for approximations for eta epsilon in H1. And clearly, from this estimate, we obtain the required estimate for the L2 norm of the difference. For phi epsilon estimate is very simple, and so we prove this lemma 2. And theorem 3 is now proved. About theorem 5, the proof is simple. We simply take the estimates of theorems 3 and 4 for a fixed zeta and obtain some appropriate resolvent identities. And finally, I would like to say a few words about application to parabolic problems. So, such two parametric error estimates can be applied to the study of homogenization of initial boundary value problems for parabolic systems. Clearly, if we study the parabolic systems in operator terms, we have to approximate the operator exponential with respect to two parameters, epsilon and t. And we use representation in terms of the contour integral of the resolvent. Where gamma is appropriate contour in the complex plane, like this. Here is theta. Then, if we apply the results of theorems 3, 4, and 5, two parametric error estimates, we can derive estimates of right order with respect to epsilon and t for the exponential. Especially, it's important to have right order estimates for large zeta in order to obtain right order estimates for small t. And the parabolic problems have been studied jointly with Yulia Meshkova, who is here. Thank you very much.
Any questions? So for the parabolic problems, you end up with operator estimates.
Yes, operator estimates.
Pointwise and t, right?
Both in the L2 operator norm and from L2 to H1. In L2,
Exponential decay.
Exponential decay, it will be exponential decay, yes. Exponential decay. Okay. Because for Dirichlet case, the operators are positive definite. And also, we have estimates from L2 to H1 with the corrector.
About hyperbolic problems.
Hyperbolic problems. We have only one result with Mikhail Slavonovich Bierman. I think you know the results in the whole space for hyperbolic equations and for non-stationary Schrödinger equations. In a bounded domain, we didn't study hyperbolic problems.
Any other questions? Yes.
So in the estimate 6, in theorem 4,
Yeah.
so if I set zeta equal to -1, then this suggests an estimate of order square root of epsilon, right? But you
Yes.
had, is it right that you had a,
Zeta equal to -1, it will be square root of epsilon.
but early, if I remember correctly, is this right that you had the result where you have an order epsilon estimate, right, for a fixed zeta?
Yes, but the constant depends on zeta.
Yeah, sure. So here it's due to the fact that this is uniform in zeta, right? You have square root,
Yes.
the square root of
Theorem
epsilon.
4 it's the same as in theorem 3. The modulus of zeta is greater or equal than 1 and non-positive.
Okay.
Zeta is non-positive and the modulus is greater or equal than 1.
And so is this sharp, square root of epsilon?
Yes, yes, it's sharp. If you take the character and if you wish to have this epsilon, then the norm of the character in L2 is estimated exactly by epsilon divided by the square root of the modulus of zeta. Yeah.
This is a boundary layer, right? Classical boundary layer, H1 norm, epsilon square root. Would not improve.
So it's sharp for if you want to have this epsilon, then estimate is sharp for large zeta. Yeah. Estimate 5. Estimate
With the
5.
character you can't.
Yes, boundary layer character, epsilon square root is in the classical.
I think Leonid has a question.
Yeah, suppose we are in RD, and I want to approach real axis sort of closer than outside of the sector. So your estimates are sort of even better than uniform, right? You have modulus of zeta in the denominator.
Yeah.
Suppose I just care about uniformity in zeta. I don't care about improvement. Can I do better than the sector? For example, sit outside the parabola.
This is true for any phi, but the constant grows for small phi.
Yes, precisely. So I want to reformulate it. Okay, so maybe if you
Outside
tell
of
me what-
parabola, we cannot prove such estimates. In fact, all these constants can be written explicitly. It's something like 1 over some power of the sine of phi to some power.
So which power?
Which power? The power is different. In fact, the power is different for estimates in theorem 3 and theorem 4.
So
In
RD.
theorem 3, it's 5. It's 5. Of course, this is here. Yes. Here we have one in the same constant.
No, I want RD, so theorem 1. Which is power in theorem 1?
In theorem 1, it's squared.
Okay, thank you.
In RD, it's squared. And in a bounded domain, it's to the power 5. Of course, it's not sharp with respect to phi.
Yeah, I think it's time for a break. Now let's thank the speaker again.